Yeah, I think by now you understand what is the properties about the proper binary trees. And the binary tree ADT, it means the abstract data type. We can look at more details on the methods, like we can know what is the left of the P is the position, and then what is the right of the position, and what is the sibling of the position. So when we do with the proper binary trees, or with the binary trees, we can have another kind of traversal. So do you still remember what is traversal? What is traversal? So the traversal means visits the node of a tree in a systematic manner. So we want to visit the nodes at least one time, and it should be in the systematic. The meaning by systematic, yeah, we will visit one by one, maybe from the left to the right, or maybe from the bottom to the upper side, and so on. So we have the binary tree, and you already know about pre-order traversal, you already know about post-order traversal. Now there is another kind of traversal, we call it in-order traversal. In an in-order traversal, a node is visited after its left subtree and before its right subtree. So we can draw a binary tree like this one. So the node is visited after its left subtree. So we call this is the left subtree. This is the right subtree. We have this is the left subtree. This is the right subtree. If you look at this one, then we will go to the first. This is number 1, and then this is number 2, and then this is number 3, number 4, number 5, number 6, 7, 8, and 9. We call it the XV is the in order rank of V, and then we have YV, it means the depth of V. We can just make the algorithm like this one, in order V. So if the V or the vertex or the node has a left child. Okay, so let's start with this one. This node has a left child. Yes. Then let's do in order left of V. So let's in order left of the node of the root. Then we will check this one. So we will call again the function, or we call this is the recursion. In order V. So now we will check. V has a left child. Yes. Then in order left of the V. So we will go here and then do the recursion. And then now we are doing the in order V. In this node, do we have any left child? We don't have any left child. So we will visit. So we visit this node. That's why this is the number 1. And then after we visit, we will check. We has a right child? Is there any right child? No. Then, because if we don't have anything to do with this one, we will return back to the previous node. Is there any more of the left child? No. We know that in the proper binary tree, we have only left and right. So there is no loop. We have only two conditions. If there is no left, of course, we will check the right. But in the middle, we will do this. So this is the in-order premise. When we do with the arithmetic expression, we can make this kind of algorithm. So this is the specialization of an in-order traversal. When we do with the in-order traversal, we will visit the left node first, and then go to the upper side, and then check the left, and then check the right, and then go back, and then check the left, and then check the right. Now we can do this with the arithmetic expression by printing the operand or the operator when we visit the node. So the idea is the same. We will check the left child and the right child. But if we know that it is the left child, we print the parenthesis. And then we go to the in-order. So the in-order, it was the previous one. If we know that this is the element in the left already finished, no other element on the left, then let's print the element. And then we will check, is there any right child? If there is any right child, then we will go to right child, and then we will do the in-order. So if we finish with everything in the right, then we will close with the parenthesis. So this is the opening, and this is the ending of one operation. So this is the extension from the in-order traversal. We can also use the post-order traversal to evaluate the arithmetic expression. We use the recursive method, returning the value of the subtree. And when we visit the internal node, combine the value of the subtree. So do you still remember what is internal node? When we visit the internal node, it means there will be another child that we will select. That's why when we do with this arithmetic expression, we can have another algorithm. We call this is the eval expression. And let's check the V. If V is leaf, you still remember what is leaf? So if there is no child, or if it is a leaf, then let's return the element. But if we have child, we will check what is on the left. So the left of V will be X. and the right of v will be 1. And then let's make this variable as the operator stored at v. So it means if I'm here, I will do the checking this one, and then I will do checking with this one. So if, let's say, I'm going to eval the right v, so I'm going to eval this v, but this v actually it is not leaf. So if it is not leaf, again we will do this section. So we will check the left and we will check the right, and then we will check the operator, and it will return 5 minus 1. After we finish with this one, then we will return back to the previous recursion, and we will do this one. Okay. And then after we finish, we will check with this one, and finally we will do with this one. There is another kind of problem that we can do with this proper binary tree. We call it, this is the generic traversal of binary tree. We call it is as the Euler tool. So this Euler tool, it includes a special cases, the pre-order, post-order, and in-order traversal. We know the pre-order, it starts from the top. We know the post-order, it starts from the left. And we know the in-order, we will check every left first and then right. So it is like the combination of the pre-order, post-order, and in-order. And we will walk around the tree and visit its node 3 times. We will check on the left, which is pre-order. We will start from the below, which is in order, and we will go on the right, which is the post-order. So we will do this one. We will visit this node, and then this is the left. And after we finish to check the left, we will move to this node, and we call this is the bottom. And then we will go to the right tree, the right subtree. And then if we go back to this node, then we call this is the right or the post order. So we call this is tour because we will walk around those nodes and we will finish until the end of this tree, and we come back to the loop. So this kind of Euler tool you can apply with like the TSP because we have the same node as the starting point. We can use the kind of linked list. If you still remember the linked list, we have one node that can be connected to another node. So we can have a node that is representing an object. So let's say I have this tree. So this is tree, not binary tree, because we can have more than 2. Okay. If it is binary tree, then at most we have 2 children. But now we have more than 2. So we call this is just 3. And we know the node from the linked list means we can see the element, and now we can make a link, and the link is the link to the parent node, and there will be another link to check the sequence of the children nodes. So for example, I know that B is the root. What is root 1? As we read this one, we have element. So we can have like 3 parts. The first is the element. The second is the parent node. Where is the parent node? And the other is the sequence of the children node. So we go here. This is a kind of list to indicate this will go to this node, this will go to this node, and this will go to this node. And this node will have another 3 elements or the 3 structures. The first is the element, and the second is linked to the parent. The parent of A is B. The parent of A is B. And then we have D. The parent of D is B. The parent of D is B. And then we have F. The parent of F is B. The parent of F is B. And for the yellow color, there is no children. And we can continue with the D. D will have another link to the sequence of children. In this case, we have another 2 nodes, and it connects to C and E. And then the C will connect to the parent node, which is D, and E will connect to the parent node, which is D. C will have the connection to the parent node D, and E will have connection to the parent node D. Because this is the link structure for trees. What about if we use the link structure for binary trees? For the binary trees, we know that we can see the left and right. Then we will add more elements. So the first is the element of that node. And then we have the parent node. What is the parent node? What is the left child and what is the right child? So when you define the node, there will be 4 data members. Okay, the data members, the first data member is element. The second data member is what is the parent node. The third data member is what is the left child, and the fourth data member is what is the right child. Let's say we have this binary tree. So we can know that this is the root. So the root, we know this is the element of B, and there is no parent. And then we go on to check what is the left. The left is A. Okay, the left is A, and A has no left. A has no right child. B has the right child, which is D, and then D has the left child, which is C. D has right child, which is E. And C and E has no children. For A, it is connected to the parent B. D is connected to the parent B. C is connected to the parent D. E is connected to the parent B. So we call this is the link structure for the binary trees. Can we use array to represent the binary trees? So the answer is yes. We can store the nodes in an array. Let's think this kind of array is a list. So I have this tree. And I want to make in an array. We know that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and more. It means we can have an array with some location. Okay, like this one. So let's start with rank. Now we will check that every node P is stopped at A. A is the array, and then the index, which is inside of the square bracket, it will be rank V. What is rank V? Rank at the root, it will be 1. We know the root is node without parent. Then this will be 1. If node is the left child of the parent node, then rank of that node will be 2 multiplied by rank of the parent. So B, for example, B is the left child of A. Is it right? This is the left child of A. Then we will do the checking of the rank 2 multiplied by the rank of the parent of B. The parent of B, what is the rank? The rank is 1. So we can say that the rank of B is 2 multiplied by 1, which is 2. If node is the right child of the parent node, then the rank of that node will be 2 multiplied by the rank of the parent node plus 1. So let's see D. D is the right node. Okay. If it is the right node, then the formula will be 2 multiplied rank of the parent node. What is the parent node? A. What is the rank of A? It is 1. 2 multiplied by 1, and then we have plus 1. So 2 multiplied by 1, which is 2, plus 1, then the result is 2. Then the rank of D is 3. So with that formula, if we have a kind of array, in the list we will start from the index Q. And then we will have index 1, we will have index 2, we will have index 3, we will have index 4, and so on. Then for the index 1, it will be the node A. For the index 2, it will be for the node B. For 3, it will be the index of D. Okay. Now, let's see about E. What is E? How can we calculate the rank of E? E is the left. Okay. Since E is the left, then I need to check 2 multiplied by the rank of the parent. Rank of the parent node is 2. And it will be 2 multiplied by 2. So the rank is 4. And in the index 4 of the array, I will put E. Let's check F. What is F? Is the right node. Because it is the right node, we will use this formula. It is 2 multiplied by the rank of the parent node. So 2 multiplied by the rank of the parent node, which is 2. So 2 multiplied by 2 plus 1. Then it is 5. Then in the index 5, we can put F. My question now. What is the content of index 8? We have 6, we have 7. Okay. We have 6, which is C. We have J as the index 7. What about 8 and 9? What is the content in the index 8 and 9? Third. Yeah. In this case, we don't have any children on E. Then what is this content? Then it will be empty. Okay. Or no element. And then we will just continue to the index 10, which is G. And then we go to the index 11, which is H. So if it is a proper binary tree, then yeah, we can say like this one. Then we will have until 12, 13, 14, 15. And the other element, the other index will be empty. Okay. So this is the array-based representation for the binaries. Okay, any questions? No question. I will continue to the next chapter, which is about the priority queue. So in the priority queue, I think you already know about queue, but we want to know what is the meaning by the priority. And we will check what is the sequence-based priority and then the priority queue sorting. Priority queues. So the priority queue stores a collection of items, and the item, we call it is a pair of K and B. K is key and B is value. So the main methods of the priority queue is add, print. So you know, whenever we have the ADT, there are two basic operations. Do you still remember? We have insertion and deletion. Okay, so this is the two basic operations in every data structure. In stack we know we have push and pop. In the queue, we have SQ and DQ. Okay. And then you can look at the linked list. In the linked list, you can also have add and remove. So the same with this data structure in the priority queue. There are two main methods. The first method is add. It means I'm going to insert an item with key of k and the value of x. So there are two parameters. And then remove. It means I will like to remove the element and remove and returns the item with the smallest key. There can be another additional methods. For example, I want to know what is the minimum. So it just returns the minimum value, but it will not remove it. So I can know what is the item with the smallest key. And if I want to know what is the length, so how many items in the priority queue. And I want to check whether the priority queue is empty or not. So there are many applications of the priority queue. Standby prior. So the standby flyers, it means if you give the flyers to the customers. So the first one can be the flyers that you will give to the customer. Or maybe the more realistic example is auction. So whenever you do auctions, the best price will go to the customer. Or the stock market. So if you know the stock price is high, and then of course you want to buy or you want to sell. So there is a kind of priority whenever you do this kind of queue. For example, let's say I'm using the P, and P is an empty element. I think by now you know that the curly bracket, it indicates the two kind of data structure. You still remember? Yeah. So the first is set, and then the other is dictionary. Okay. If it is a set, then you cannot have multiple. You cannot have the redundant item. So the item will be always unique. If it is dictionary, you will have the key and value. Okay. So like this, for example, I want to add the 5,8. So I have 5, 5 is the key and A is the item or the value. I want to add 9, C. So based on this priority queue, we want to check the minimum value. It means if I know that the key is smaller, it will be in front. But if the key is higher, it will be in the rear. So I'm going to add another element, 3, B, because I know that 3 is smaller than 5 and 9. So I put it in front. And I add again another element, 7, D. So 7 is in between 5 and 9. Then I put it here. If I want to check what is the minimum, then I know that the minimum is 3, B. If I want to remove the minimum, then the minimum will be remove. If I want to remove the minimum again, then it will be 5. If I want to check what is the current length, so I have 2. If I want to remove the minimum, 70. If I want to remove the minimum, 90. And if I want to check whether it is empty, yes, it is true, because now it is empty. And if I want to remove the minimum again, it will be error, because the current data is empty. Okay. Okay, let's have a break. I will continue after the break.